Am I on? Okay, we'll get started again. So now we'll delve into chapter 2, which is all about descriptive statistics. Okay, and so we first just talk about data. Okay, and so we can think of data as information that we gather on subjects. And at least in our classical view of statistics, we're going to just kind of treat our data as these tables of data, something like this. Okay. Okay. And so each row is an observational unit. Okay. And each column is a variable. So it could be something like, we're going to take information on, students, and we'll have, your name, sex, age, I don't know, what else? Number of siblings, etc. Okay? And then so we can have Joe, male, 24, 2 siblings, and Jane, female, 27, no siblings, or something like that, okay? And then you just fill out the table. Okay, and so variables can come in 2 types. In one of 2 forms. So we have numeric variables. These are also called quantitative variables. And numeric variables, they tell us how much or how many. Okay. They often carry a unit. So whether that's, pounds, years, or, siblings, etc. Okay. And you can kind of make comparative statements. Hey, Joe has 10 pounds more than Jane, okay? Or Joe has, or, in English we say weighs. But you can make these kind of comparative statements, okay? The other type of variable would be categorical variables. Okay. Okay, and we have, they can also be called qualitative variables, and these tell us what type or what kind. Okay. And it doesn't quite make sense to try to do a comparative statement between between categorical variables. If you're talking about hair color, you cannot say I have more brown hair. I don't know. It doesn't work. Okay. You'd say, you know, this is more or less, you know, it just says this one's red and this one's green and this one's, if we're talking about, I don't know, whatever, some other colors of something, okay? So categorical variables, so that would be things like gender, hair color, things that, you know, you can't make comparative statements even though they might be represented with a number. So like zip code and area code are categorical variables. If we were to gather someone's zip code information, that would be categorical. It doesn't tell you a quantity. You can't say I have 40 more zip code than you. That it just doesn't make sense. So we have that, okay? As far as numeric variables, we can also have, I guess you can further divide this into discrete and continuous variables. So I guess you can think of discrete as only certain values are possible. So like whole number values are often the case for discrete variables. Or continuous, you know, they exist on a continuum with decimals. So, you know, so something like weight would be continuous because even though we generally report our weight to the nearest whole pound, if we had a very accurate scale, we could say someone weighs 143.228 pounds and someone weighs 143.22645 pounds or something like that. So if we had very accurate scales, we could measure these things out to great precision. Whereas when we ask how many siblings do you have to give me a whole number, okay? Yes, I realize there are such a thing as half siblings, but you have to count them as a full person, okay? So so we have that. Okay, when we might want to try to summarize. So we can summarize you know, data in our table. Okay, so you know, you imagine, you know, the big kind of table of data, and rather than having, you know, if you surveyed 500 people, you'd have 500 rows, and rather than having to report the entire table, you know, we can summarize the data in our table with more tables, okay, with a summary table called a frequency table. And this one. Okay. And a frequency table can, so for categorical data, it exists for both categorical and so we can create a frequency table, and so for categorical data, it would look something like this. You would have the category, so you can have male, female, okay, and you just have the frequency. So maybe 221. 247 for a total of 468 people. Okay. And maybe you have a percentage. And so we would do 221 plus 247. Oops, I clicked something. So I do 221 divided by 468. So I get 47.22%. And then the flip side of that would be 52.78%. Okay. And you can imagine just whatever whatever data you have, you can kind of list off the things here. Okay, so this is this is summarizing. This would summarize a large data table with how many rows would exist in the original data table. For 468, right? One for every observational unit. So we have a total of 468 people in the original data table, and we've summarized it with 2 rows here. Okay? And again, this would be summarizing categorical data, right? Even though we've got numbers here, it's categorical data because we're talking about whether someone is male or female, and that's a categorical variable. Okay? Yes, question?
Yeah, let's say just for this category, male or female, would you explain to male or female with siblings or something like that?
So yeah, let me talk about for numeric data and male or female with siblings. It could be done, but generally, I was just going to show you for categorical data, and then we'll do it for numeric data. Okay. All right, and so you can imagine that the big table again, and here we can have a number of siblings. And we would list off the numbers 0, 1, 2, 3, 4, and then maybe I will just do 5 plus. Okay, so if you have more than 5 siblings, 5 or more, you'll just kind of get grouped in. And then so the total would be 468, and I'm at a loss here. I don't know how many there should be. 205, 184, 32. 47. Okay, so then maybe I'll have 12 here and 10, and that leaves 25 over here. Okay, something like that. Okay. Okay, and so here this is again a frequency table. The key difference is that when you have categorical data, okay, you can switch the order of rows. or maybe I should say row order is arbitrary for categorical data. Okay, so you know, with only 2 rows, you know, that really just means do you put the male row on top or the male row on the bottom, or you know, do you switch these rows or not? But you know, if you had 10 different categories, there's no rhyme or reason behind a certain order of categories. You know, we've kind of developed the alphabet, and there's alphabetical order, but that's also completely arbitrary. There's no reasoning really behind why the letter K should come before the letter L, which comes before the letter M, or anything like that. It's just, you know, we have certain orders that are kind of have been established, but there's not a whole lot of reasoning. If we're talking about colors, we have the rainbow order, but that there, you know, when you're making a table, it doesn't have to follow any particular order, okay? And you know, where would you put something like silver in the list, right? And so, you know, if you played with a box of crayons, like some of them you can kind of arrange in order of hue, but then you always get these like, you know, you get the brown and the gold and the silver and the white, and you're like, I don't know, there's no order for those. Meanwhile, with numeric data, you have to put them in order, okay? You can go 5 through 0. You can put the largest on top and the smallest on the bottom, or but you can't switch the rows in the middle, okay? And so this is reflected when we do graphic displays. So with graphic displays, we create bar charts. And forgive my, you know, these drawings I don't. Okay, so and we could switch these around. We just equally valid would be this picture. Okay, if we put the female and male over here. Okay, so you would write 247, 221, or something like that. So these are bar charts. Okay. On the other hand, over here, we have a histogram for the numeric data. And I'm just kind of eyeballing these numbers, so don't hold me to it, okay? I messed this up, didn't I? Something like that, okay. And so with histograms, you have to put them in order, small to smaller to large, from left to right. And students often ask why the boundary of the number goes over here and not in the middle of the bar. This is just the I guess tradition, and I guess it's more so noticeable when you have a discrete variable like this. It makes sense to have kind of histogram set up this way, especially when the underlying variable is continuous. But as far as discrete values go, we still follow. We put the number on the kind of the left edge here, and go forward like that. Okay, so this is called a histogram, and this is called a bar chart. Bar charts, we often have little gaps in the bars, gaps between bars, and over here we have no gaps, right? And there's no rule or law that says that must be the case, but kind of stylistically, this is the tradition that's been established for bar charts and histograms. Okay, are there any questions on this? The textbook also talks about you can create, for frequency tables, for numeric data, you can also create bins of your data. So with something like siblings, where most of your answers are going to be 0 to 5, generally not more than 10. Most people don't have more than 10 siblings. It's fine. But if we were talking about people's weights, okay, you'll have a large spectrum of weights. People anywhere from 90 pounds to 290 pounds or something like that, or even more. And it might not make sense to have one row for every single possible weight, okay? And so you might create bins, and you might say this bin is for people from 100 to 120 pounds, and this, or 100 to 119 pounds, and this bin is for people from 120 to 139 pounds or something. And you might create small ranges, but and the table would work in the exact same way. You would just count how many people fit within that certain range, and then you could build up your histogram accordingly. Is that good? Okay. Okay. So, if we're talking about here, let me see if I can pull up. Okay, so here we have a few histograms, okay, that the textbook drew. So they took all of these. These are 36 values of people's cholesterol levels, okay, and they created a binned histogram this way. They said basically from 20 to 39.99, the curved parentheses means up to but not including 40. And they said there was one person in that range, and from 40 to 59.999, there were 4 people, and they graphed the histogram accordingly. So from 20 to 40 is our one person, from 40 to 59.99 is there are 4 people, so on and so forth. Okay, now the shape of our histogram, we can talk about the shape of the histogram, or the shape of the distribution of data. Okay, and so here we're talking about numeric variables, right? And so you can imagine a histogram, and we can generalize the shape of a histogram with kind of these nice smooth curves here. So I'm going to just kind of copy this thing, throw it into our. Okay. So here, okay, so we can generalize the shape of a histogram with a smooth curve. All right. And so keep in mind that histograms are for numeric data. Okay. Okay. So let's just take a look. What does it mean for someone to have, I'm just going to arbitrarily draw values here. Okay, so let's say this is 0, and we'll say each bar represents 10 units. So this will be 0, 20, 40, 60, 80, 100, 120, 140, 160. Okay? So what seems to be, common values? Common values of whatever it is that we're measuring here.
Values between 20 and 60.
Okay, values between 20 and 60 seem to be quite common. Okay, so 20 to 60, or 10 to 60, or whatever, however. So let's just say 10 to, I don't know why I put a $sign there. 10 to 60 are common values. Okay. Where the most common is something between 30 and 40. Okay, 30 to 40. Is most common. Okay. Do we have people out at 150? Do people exist that have scores of 150? Yeah, but not very many. Okay. People do exist. With values of 150, but not very many of them. Okay, so keep that in mind when if we are summarizing some histogram with the shape like this. Okay. So what this is saying is that values from here to here are most common. Okay. People out here exist. But not very many. Okay. If we want the other direction, does anyone exist out at like -40? No, so no one out here. Okay. All right. So we would say this shape, we give it a label and it's called skewed right. Okay. And so skewed right means most people are kind of, near this hill, but you have outliers, or you have people with values much higher than, quote, normal, whatever, or typical might be considered. Okay, so you have values much higher than typical, but you have no one much lower than typical. Okay, so whatever typical is, in our case 10 to 60 or 30 to 40, you can have people, at 100 points higher than typical, but you have no one 100 points lower than typical. So most are, quote, typical, and the skewed right part is the values exist much higher than typical. No one exists much lower than typical. Okay. So examples of things that are skewed right. Numeric. We're talking about numeric variables here. So things like income distribution is skewed right. You know, most people make between, I don't know, arbitrarily 20,000 and 100,000 a year. Okay. Some people make $1 million a year. Okay, $1 million a year would be 900,000 more than the upper edge of typical. Okay. To make 900,000 less than typical would take us down to like negative 800,000 or negative 80,000, okay, or 920,000, whatever it is, okay, and no one makes that much negative money, okay. People don't have it. It's impossible to have a wage of negative $800,000 per year, and so this would be something that is skewed right. All right, and so we have these other shapes for distributions, and just keep in mind that when I draw a curve here, we're kind of just summarizing a histogram which represents a numeric variable underneath. So this would be skewed left. Okay. We have symmetric. These are would also be called unimodal because it's got one peak. And then you can have something that looks like this. This would be bimodal. Okay. Can you think of something that might be bimodal? Okay. So remember we have to these are numeric distributions. Okay. So things like I don't know, things like gender or whatnot would not count because those are categorical variables. So bimodal, we might see something bimodal for maybe like testosterone levels, though. Okay, so yeah, I don't know what testosterone levels would look like, but it would probably be bimodal in that you would have. So everybody produces some testosterone in their body, okay? And in general, males produce much more testosterone than females. And so, you know, this around here would probably be the, quote, typical male testosterone level. And this over here would be our typical female. Okay, and so you'll have people over here. These would be individuals, so probably men that have very high testosterone, even compared to other men. And over here you would have males that produce less testosterone than the typical male. Okay, over here you would probably have females with testosterone that's higher than the typical female, and over here would be females with less testosterone than the typical female. And then kind of in this middle-ish zone, you would either have women with very high testosterone or men with very low testosterone or something like that. and I have a feeling, and don't quote me on this, but I think the difference is much more pronounced between men and women, but I actually, I don't know. I'm not a endocrinologist, so. But I remember. Do you remember Caster Semenya, his Olympic athlete? Anyway, she was a runner, and she totally did amazing, and her competitors accused her of being a man, and so the way they resolved it, and yeah, I guess with modern technology, it's not the way to resolve someone's gender or sexuality is not so clear cut and simple anymore, and so it came down to basically a hormone level test, and she had the quote correct amount of hormone to be a female, and so they let her championship stand and things like that. But that's what a terrible thing to accuse someone just because you lost, right? Anyway, okay, we'll continue on here. So the important thing to keep in mind again is that when you see these, when we talk about distributions of these variables, we're talking about a numeric variable, and you want to keep in mind, what does it mean to be on the let me just what does it mean to be on the left tail over here? So this would be skewed left, and this is the left tail. What does it mean to have a value that's in the left tail in this case? Yeah, you have very low values comparatively to the other people, okay? And this would be the right tail and left tail, and so if my picture were good, the left and right tail would be equally sized here. Okay. So we will continue on with numeric summaries. Or numeric variables. Okay, so here we're dealing with numeric variables, and we are trying to summarize a set of data, whether it's the 500 people in your table, or it could be a million people, or just a group of 20 or whatever. You have a bunch of people or a bunch of data points, not necessarily people. And rather than listing off every single bit of data, you want to summarize it. And so numeric summaries allow us to kind of group it up into just a few numbers that give us the key points. Okay, and you guys are familiar with numeric summaries, and but we have to keep in mind that numeric summaries, because they are summaries, they don't tell the whole picture. Okay, if you ever read a summary of a book, you miss out on details that may or may not be important. Okay, the book summaries try to capture what's important, and in our when we report numeric summaries, we're hoping that they capture what's important, but they might miss out on some key points. Okay, so you're familiar with numeric summaries in your own life, like your grade point average. Okay, your GPA it's supposed to summarize your entire academic career into a single number. Okay, and so because maybe people don't want to know how you performed in every single one of, maybe you took 40 classes over the course of time. People might not care how you performed in every single one of those classes, but if you say, oh, well, my GPA is a 3.9, that gives them a very good picture of your academic performance. And they go, oh, okay, well, you've done very well. Or, you know, someone else could say, you know, I have a GPA of a 2.1, and that it also gives you another picture of the student's academic performance. And, you know, of course it doesn't tell everything, and so, you know, it could be, you know, you could have two students, one with a 3.5 and one with a 3.6, and, you know, maybe one student took easier classes, or, you know, one student had to work throughout college or something, and all, you know, all sorts of stuff, and the numeric summary doesn't capture that. But what it does is it summarizes a whole bunch of numbers or a bunch of data into a single number that is useful to us, because it allows us to kind of make these quick comparisons between groups of data. Okay, and so that's the power behind numeric summaries. When we're dealing with samples of data, we often will boil down a sample of data down to just one or two numbers and use that to kind of get a sense of the data without necessarily looking at the individual data points themselves. Okay, these are useful for summarizing a set of data with one or a few numbers. Okay, most useful for making comparisons between groups of data. Okay? And so, you know, you could have, we have different numeric summaries for different different things. So for school, we have the GPA, and depending on which school you go to, you know, they might calculate your GPA in different ways. And in high school, you know, maybe your school weighted honors classes to be 5 points and things like that, and that made you say, well, I don't want to take any PE because the max I can get is a 4, whatever. So we have different formulas for different situations to kind of compare economic prowess. We have you know, GDP and GDP per capita for different countries. You know, you have the Gini index, and you know, the Human Development Index, and these are supposed to be numbers that say, oh, you know, Norway is doing great, and you know, this, you know, like Sudan is not, or something. And these are just the numbers that are supposed to kind of capture what how developed a country is or something. And so we have these customized numeric summaries for different purposes. And then there's these kind of just numeric summaries that can be applicable to almost any scenario with numeric variables. And so we'll learn these generic ones, and they're like the mean and the median, the standard deviation, and these are just other numeric summaries that can be applied in these generic scenarios. Okay, so we have custom numeric summaries. Okay, so for almost any purpose you can think of, there somebody probably has some customized numeric summary. So, you know, Human Development Index, or you know, NFL passer rating, whatever it might be, okay, etc., etc. Okay, and then we have just kind of these generic numeric summaries. Okay, and so and all of these numeric summaries serve different purposes. Okay, the generic numeric summary here that we're going to talk about, we have the mean and median. These tell us kind of where the center of our data lies. All right, so the mean can be thought of as the balance point. Of our data. Okay, and so, for example, let's say we had these data points, 11, 13, 19, 2, 10, and 1. Okay, and so I'm going to just draw a number line here. 1, 2, 3. Okay, and I'm going to just imagine me putting a brick at each of these numbers. 11, 13, 19, 2, 10, and 1. Okay? So imagine this being kind of a plank. Where would I need to put, where should I put the fulcrum, the little triangle, so that this thing would stay balanced in the seesaw? Okay? Well, the place I would position it would be right here, and this is the location of the mean. So the mean is equal to, I would add all of these up and divide by 6, so the symbol for the mean is y bar, and we take this by adding up each y and dividing by how many we have. So in our case we would do 11 plus 13 plus 19 plus 2 plus 10 plus 1 divided by 6. We would get 56 over 6, 9.33. So my mean is 9.33. This is our balance point here. Okay. The median, on the other hand, is the halfway point. Okay. And so the median, we would say, I arrange these from least to greatest. Where is a spot where half of the numbers are greater and half of the numbers are smaller? And we would draw the median in between 10 and 11, because we have 3 data points that are 10 and smaller. We have 3 data points 11 and larger. So the median is the halfway point. Okay, spot where half are greater and half are less. So the median here would be go right there. All right. Is that okay? And And so if you have larger data sets, this diagram, by the way, is known as a dot plot. Okay, I drew little boxes, but you know, if you got more data points, you probably just put dots. And oh, has my audio been off for a very long time? No, I don't know. You guys can hear me still? Okay, well, I got it just said low battery warning right there, so, okay. You know, we can build dot plots, and depending on how much data you have, they can be useful. I don't know. So this would be a dot plot, and they're similar in histograms, except you have individual dots drawn out. So another graphic display is called a box plot. Okay. Okay, and a box plot this might be called a box and whisker plot also. And a box plot looks something like this. Okay, you have a box, and then you have two bars proceeding from the box. And so the boundaries of the box, box is defined by three spots. In the middle we have the median. Okay, and over here we have Q1, Q3. There are invisible boundaries out here and here, and this would be the upper fence and lower fence. Okay. And so here, this would be the largest data point within the fence, and over here would be the smallest data point within the fence. Okay, and then out here, these are outliers. These are any data points outside of the fences. Okay, and so you can have outliers that are smaller than the data as well. I mean, smaller than the lower fence. So you can have outliers on either side. Okay, so what is, maybe we have to define what Q1 and Q3 are, but
I was going to ask, what defines the upper or lower fence?
yeah, so we'll talk about what all of these, where the fences are and where Q1 and Q3 and all of this stuff is, okay? Alright, but I just want to have you guys have this diagram first. Okay, so we've already defined the median. The median is the halfway point, so spot where half of the data is larger, or I'll say half of the data is less and half are larger. Okay, Q1, this is the spot where 1/4 Okay, Q1 is known as the first quartile, the spot where 1/4 of the data is less. Okay, Q3, third quartile. This would be the spot where 3/4 of the data is less. Okay, and then we define something called the IQR. This is the interquartile range. And this is equal to Q3 minus Q1. Okay, so Q1 is maybe it's easier for us to think of percentiles. Q1 would be the 25th percentile. Okay, where 1/4 or 25% of the data is smaller than Q1. And Q3 would be the 75th percentile. And the IQR would then be the distance from Q1 to Q3, or the difference between the 25th and 75th percentiles. Okay, so that's the IQR. And then the upper and lower fence then, these are, so I'll write this, the upper fence is equal to Q3 plus 1.5 times the IQR, and the lower fence is equal to Q1 minus 1.5 times the IQR. Okay, so you take the width of your box is basically the IQR, right? Q3 minus Q1, that's the width of your box. And you go out, 1.5 times that. So you take that width of the box and you go, here's 1. You go from Q3, go out 1, and then 1.5 times that. And that takes you up to the upper fence. And then if you take the width of this box and you go out 1.5 times below that, that takes you to the lower fence. And that kind of defines what's an outlier and what's not an outlier. Okay. So we'll try building a box plot with a set of data, and we'll see how we do. Okay. All right, is this okay? Okay, so we're going to, so here we are looking at Radish growth data. And I'm going to put these in arranged in order from least to greatest, okay? Okay, so here I guess we planted some radish seeds, and we left them growing in total darkness, and some of them grew a lot and some did not. So this is what we have. Some grew 8 millimeters, 10 millimeters. This is after 3 days. 15. Okay, so we have 14 radishes. This might not have been the data set I wanted. Okay. All right, and then so let's figure out where our median is. Median, we'll figure out where our Q1, and we'll figure out where Q3 are. Okay, so if I have 14 radishes, how many will be larger than our median and how many will be smaller than our median? Right? 7 and 7, right? So I'm going to count 1, 2, 3, 4, 5, 6, 7. These have already been placed in order from least to greatest. So our median will go right here. So our median is equal to what? 21. Okay, so it's just halfway between these two numbers that separate the 7 larger from the 7 smaller. Okay, so to get Q1, basically I'm going to just take my 7 smaller numbers and find the median of those numbers. Okay, so basically, you know, to get a quarter, you know, if you have a loaf of bread and you want to cut it into quarters, you would first cut it in half and then you cut each half in half again. So here I've got 7 numbers and I want to find basically the median of these 7, and what will that be?
15.
This one right here, okay? So this is Q1 because now I have 3 numbers that are smaller than it and 3 numbers that are larger. I did the same thing over here, and what do I get? Q3. Okay, so Q1 is 15, Q3 is 30. Now if I had an even number, the Q1 would be halfway in between 2 numbers over here, and then if I had an even number over here, Q3 would be halfway in between 2 numbers over here, right? Okay, so what is my IQR?
15.
Yeah, 30 minus 15. So I have an IQR of 15. So my upper fence would be at 30 plus 1.5 times 15. And then my lower fence would be 15 minus 1.5 times 15. Okay, so this would be at 52.5. And this would be at negative 7.5, I believe. Okay, so are any of my data points outliers? No, right? The largest data point I have is 37, so I have no outliers, no data points larger than 52.5. Okay. And I also have no data points less than negative 7.5. So no outliers. So when I draw my box plot, I'm going to have to draw a number line here. And we'll start at 0, 1, 2, 3, 4, 5. This is not going to work. 10, 2, 4, 6, 8, 20, 2, 4, 6, 8, 30, 2, 4, 6, 8, 40. Okay. So so let's see, Q1 is at 15, so I draw a line right there. My median is at 21, and my Q3 is at 30. Okay, so this is my box right here. And then the lower bound goes down to 8, or the my lower whisker goes to 8. And my upper whisker goes to 37. So that's like right here. Okay? And then yeah, my fences are all the way out at 52. I don't have to necessarily draw these. But I would, I would have an upper fence and a lower fence down at negative 7 or something like that. Okay? So I have no outliers. This is just what my box plot looks like here. Any questions on the box plot? Okay, so so box plots are useful to kind of illustrate very quickly the highlight, the key points of a distribution. So you've got a data set, and you can just kind of boil it down to just kind of these 5 key anchors, and you can compare, one box plot to another box plot very easily, just because there's really only 5 spots to look at. The boundaries of the box, the edges of the whiskers, maybe some outliers if they exist. Okay. We'll go back to numeric summaries, and so we talked about the mean and the median as far as numeric summaries go, and we have some numeric summaries that measure spread. Okay. And spread, or dispersion, is this concept of our data points, are the values in our data, are they similar to each other, or are they vastly different from each other? Okay. Okay, so you can just think about, ages, the ages of students in a college class, okay, or even a class like this, and not everyone is the same age. Not everyone was born on the same day at the same time, so everyone has different ages, and in terms of, as far as the range of ages go, we'll see some variation here. Okay. Meanwhile, think back to maybe your high school history class, and everyone in that class was probably in the same grade and the same age. Okay, so probably everyone in that class was born in the same year. Maybe you had a student who skipped a grade. Maybe you have a student who was held back. But by and large, almost everyone in that class was probably born in the same year, in the same grade. Okay, so in your high school history class, the spread in terms of ages is very, very small. Okay, you do have variation. Not everyone's still exactly the same age, but you've got a small amount of spread. And your typical college class, you're going to have more spread than that. Okay, and then if you go to like a continuing education center where you have people coming back after many years away from school, you're going to have even more spread, because you're going to have quite a wide range of ages there. Okay, so so spread is this concept of, are the values quite similar, or are they quite different, and so that can be applied to ages in a classroom. It could be applied to almost any other set of numbers that we have. Okay, so just here's an example. Okay. Ages in a college class versus ages of students in a high school class. Here you'll have less spread. Okay, nearly everyone has a very similar age. And over here, much more spread. Okay. larger variation in ages. Okay? And so we have numeric summaries that basically assign a quantity to this concept of spread. So rather than just saying this has less spread, this has more spread, we can assign a numeric value to the amount of spread that we have. Okay? And so some of these are simple concepts. Okay? We've got the range, and this is just the difference between the lowest value, or the least, I'll say lowest value and largest value. Okay, so range is equal to, actually I should write the max minus the min. Okay. And then we also have the IQR, or the interquartile range. And this is the difference between Q3 and Q1. So this tells you how far apart the 25th and 75th percentile are. And these give you a good idea of the amount of spread in your numbers. And so whereas the range is very much affected by the extreme values. So if you just, if almost everyone is within a certain within a certain range, but you have one individual that's much smaller and one individual that's much greater, that's going to show up in the range. Whereas the IQR does not care about the extreme values, and so those things will not show up in the IQR. And so depending on your situation, you might want to report the range, or you might want to report the IQR. It depends. These things make a difference and matter. We also have the standard deviation. Okay. And the standard deviation is just another way to report the amount of spread. Okay. And this can be thought of as, well, let me just say the standard deviation is the square root of the statistical quantity called the variation. Okay, and the variation can be thought of as, quote, the average squared distance from the mean. Okay, and so let's maybe I'll try a simple example here. Okay, we'll have I have 1, 2, 3, 4, and 10. Okay, and so we have to, I think I did this right. 1 plus 2 plus 3 plus 4 plus 10. Yeah. Okay. So here, the mean, we have 5 numbers. And the mean would be 1 plus 2 plus 3 plus 4 plus 10 divided by 5. I have a mean of 4. Okay? And so if I were to draw these out on a number line, 1, Okay, I'm going to put little dots here. Okay, so our mean goes right here. This is where our thing would be balanced. So then we can ask each number, how far are you from the mean? Okay? So the distance from the mean basically I can just subtract 4. So how far is 1 from the mean? It's 3 units away. Right? This is 3 away. How far is 2 from the mean? It's 2 units away. How far is 3 from the mean? It's 1 unit away. How far is 4 from the mean? It's at the mean, so it's 0 units away. And how far is 10 from the mean? 6 units away. Okay? So these are the distances from the mean. And we just got these basically, you know, subtract the mean from each value. Okay. And then we're going to square those distances. Okay, so squared so if I square each of those distances from the mean, 3 squared will give me 9. 2 squared will give me 4, 1 squared will give me 1, 0 squared will give me 0, and 6 squared will give me 36. Right? I guess I could draw this. This is 6 units away. Okay? And we would, quote, take the average, but it's a little bit different. We add these up, and rather than dividing by 5, we divide by n minus 1. Okay, so we quote take the average, but this involves add them up and divide by n minus 1. Okay, and the reason why we divide by n minus 1 is it's called Bessel's correction, and it's because we're treating this as a sample taken from the population. You don't have to worry about the mathematical reasoning behind that, but we're going to add these up, and rather than divide by 5, we divide by 4. Is that okay? All right, so we're going to do 9 plus 4 plus 1 plus 0 plus 36, and then we divide by 4 rather than 5. So I get a quote average of 12.5. This is my variation. And then the standard deviation will then be the square root of this. So I get a standard deviation of 3.56. I'm sorry, 3.546. Okay. And that is the standard deviation. Is this okay? So the steps in getting this, there's a few steps involved, but the key here is to keep in mind that the standard deviation is it's another way to measure the amount of spread or dispersion in a data set. Okay, and spread is just the concept of, are my numbers quite similar to each other, or are they quite different? All right. So if, for example, if I had another set of data, and those numbers were 1, 2, 3, 4, 5, how would the standard deviation of this set of numbers compare to this?
It'll be smaller.
It'll be smaller than 3.546, okay? And here I have some software that can just kind of calculate the standard deviation very quickly. So here I can just say A is 1, 2, 3, 4, 1, 2, 3, 4, 10, and indeed the standard deviation of A is what we calculated. And if I ask for, if I replace the last number with 5 instead of 10, the standard deviation of this set is 1.58. Okay, so you know, the set of numbers 1, 2, 3, 4, 5 would have a standard deviation of 1.58, and over here we have a standard deviation of 5355. I don't know why I wrote a 4 here. 536. Okay, so it's just, you know, are the numbers spread out? Are they similar to each other? Okay. So you have a few exercises in your textbook going over that, and I think that's all we'll cover for today. Most of the time I go all the way until 10 o'clock, but today we'll end a few minutes early. So we'll see you guys next week. All right, have a great week.